Hi, welcome to Algebra 2 Common Core. In our new unit, we're going to be learning about rational functions. So let's start with the definition of a rational function. You might need to pause the video to write down the definition. A rational function is a function of the form f of x equals p of x over q of x, where p of x and q of x are both polynomials. So most of the time we're going to say that a rational function is a fraction function. Let's take a look at some examples of rational functions. I might have the function f of x is equal to 2x plus 5 over x minus 4. Another rational function, how about g of x is equal to x squared plus x minus 10 over x plus 2. Or I might have a function like h of x is equal to 6 over x squared minus 2x plus 5. All of these are rational functions because they have a polynomial in their numerator and denominator. In the case of h of x, the numerator is 6, but that's just considered a monomial. Now what's going to be common to all rational functions is that the graphs of rational functions have what we call asymptotes. So we're going to get used to drawing and talking about the asymptotes for rational functions when we're making their graphs. An asymptote is going to be a line that a graph approaches on the ends. So if we take a look, and you can enter this in your calculator, so pause the video for a minute and come back with the graph of y equals 1 over x minus 2. On your calculator, you should see that there's a line that the graph comes very, very close to. In this case, the line is at x equals 2. So if I've got the number 2 right here, at 2 I don't have any function value. The other line that this graph comes very close to is the line y equals 0. Y equals 0 is a horizontal line that is the same as the x-axis. So graphing this, I see that I have a graph that looks something like this, and like this. And the asymptotes would be these horizontal and vertical, I said that the wrong way, here's horizontal, here's vertical lines that the graph gets very close to when I'm looking at the ends of the graph. Now do me a favor and take a minute to graph the second example and put it on these axes. You can again use your calculator. Make sure that when you're entering it into your calculator you've got parentheses around any binomials. So come back when you have a sketch of that and compare with mine. Your graph should look like the one that I've sketched. You'll notice that I have two vertical asymptotes. We abbreviate vertical asymptotes with the letters VA. And those are occurring at x equals positive 2 and x equals negative 2. We also have one horizontal asymptote. That one is the line y equals 0. So on our graph, here are my vertical asymptotes. Here's my horizontal asymptote. And again, you'll see that at the ends of the graphs, whether it be on the right or left-hand end, or as the graph is getting very small or very large, the y values, or the outputs, are approaching those asymptotes. In example number 1, let's consider the rational function given by f of x equals x plus 6 over x minus 3. We'd like to examine some of the properties of this function and ultimately its graph. So in part A it says let's algebraically determine the y-intercept for this function. Well, from previous work in this class we know that the y-intercept is going to be the place where the x is equal to 0. So I want to find f of 0. Let's substitute 0 in for x, so we have 0 plus 6 over 0 minus 3. And when we divide 6 divided by -3, this is giving me -2 as my answer. So my y-intercept is going to be where x is 0, y is -2. In part B, let's algebraically determine the x-intercept. So for the x-intercept, that's going to be where y is equal to 0. So my function value, or my output, has to be 0. So I'm going to say 0 is equal to x plus 6 over x minus 3. Now one way of doing this is to multiply both sides of the equation by x minus 3 so that I can cancel off that denominator. But when I do that on the left side, 0 times x minus 3 just gives me 0. On the right side, the x minus 3's cancel, so I have x plus 6. So x is equal to -6 is going to be my x-intercept. That would be the point with coordinates -6, 0. For part C, we want to find the values of x for which this function is undefined, and why does it turn out to be undefined. Now we should remember that word undefined as meaning the denominator is equal to 0. So looking at my denominator, I have x minus 3. I'm going to set x minus 3 equal to 0 to find out where the denominator is 0. If we add 3 to both sides of the equation, I have x equals 3 is going to be where this graph is undefined. Now we could also take a look at our table of values on our graph, on our calculator. So if I look at some of the y values, for example, when I look at when x is 0, I know that y was -2. If I plug in a 1 for x, I'm getting 7 over -2. If I plug in a 2 for x, I'm getting 8 over -1, which is -8. And when I plug in a 3 for x, on my calculator I can see that it says error. And that's because my graph is undefined at that spot. Now what ends up happening is that place where the equation, where the function is undefined, is actually going to be our vertical asymptote. So this is how we're going to find the vertical asymptotes, by setting the denominator equal to 0. But the vertical asymptote and the place where the function is undefined also helps us to identify the domain of the function. All we're going to say here is that we can have any x value except for the number 3. We saw that on our table of values. At 3, my graph didn't have a function value, there was an error. So in set builder notation, we can write this domain as x such that x cannot equal 3. So x can be anything except for 3. In interval notation, taking a look at the graph, the only number I can't have in my domain is the number 3. I can have anything bigger than 3. I can have anything smaller than 3. So in interval notation, we could go from -infinity to 3, and we could go from 3 to infinity, but 3 is not included in the domain. Let's practice these very same ideas in example number 2. So for the function h of x is equal to x plus 5 over 2x squared plus 11x minus 6. What I'd like to do is first of all find where this function is undefined. So in part 1 here, we are going to set our denominator 2x squared plus 11x minus 6 equal to 0. Now this is a quadratic equation, so I now have 3 different possibilities for solving this quadratic. I can factor it and hope that it's factorable. I can, of course, use the method of completing the square, or now, from our last unit, I know that I can solve by using the quadratic formula. So I might practice that again and say, let's make my a, of course, be equal to 2, b is equal to 11, and c is equal to -6. So x is going to be equal to the negative of 11 plus or minus the square root of 11 squared minus 4 times 2 times -6 all over 2 times a, 2 times 2, which is 4. So x is equal to negative 11 plus or minus the square root of, and if I type this into my graphing calculator, I'm getting 121 plus 48, which is 169 divided by 4. This, of course, gives me my two solutions. One is going to be negative 11 plus 13 divided by 4, and the other one will be negative 11 minus 13 divided by 4. So one solution will be x equals 1/2, and the other solution will be x equals negative 6. So these are the two values where my rational function is undefined. Now that is also then going to tell me what my vertical asymptotes are. So the vertical asymptotes for this graph will be x equals 1/2 and x equals negative 6. So finishing off now with the domain of the function, I'm going to say that my domain is going to be the set of all x values such that x does not equal 1/2 or negative 6. Now if I set that up in interval notation, that means I would be looking at a number line and I would say the domain would be the set going from negative infinity to negative 6, and then the set going from negative 6 to 1/2, and then the set going from 1/2 to positive infinity, just not including those numbers negative 6 and 1/2. Let's take a look at the second example. G of x is equal to x minus 1 over x cubed minus x squared minus 9x plus 9. For part 1, I want to find where this is undefined, so I want to set my function denominator equal to 0. Now you can either recognize this as a factor by grouping or factor using your box method. So I want to set this polynomial equal to 0. So putting it into my box, I've got x cubed minus x squared minus 9x plus 9. In my top row, I've got a common factor of x squared. Bottom row, negative 9. First column x, second column negative 1. So what this then tells me is that I can factor this into x minus 1 times x squared minus 9 equals 0. Go ahead and factor the x squared minus 9. So that's going to be x plus 3 times x minus 3. Setting all three factors equal to 0, I see that I have three places where this function will be undefined. X is equal to 1, x is equal to negative 3, and x is equal to 3. So in part 2, those are going to be my vertical asymptotes. X equals 1, x equals negative 3, x equals positive 3. And of course then that means that my domain is going to be the set of all x such that x cannot equal 1, 3, or negative 3. In example number 3, we've got the function f of x is equal to x minus 3 over x squared minus 6x minus 16. And again, this time we'd like to find the domain. So our domain completely depends on where this function is undefined. Setting my denominator x squared minus 6x minus 16 equal to 0. This is a nice easy one to factor. So we're going to say x minus 8 times x plus 2 equals 0. Now when I do the t-bar on this, I get that x equals 8 is going to be one spot where this function is undefined, and x equals negative 2 is the other spot. So for my domain, I don't want to let those values of x be in my domain. So my domain then is going to be option number 3, x cannot equal negative 2 and also 8. For exercise number 4, we're going to go back to something that we haven't touched in a little while since our function chapter. We want to find the inverse of each function. So remember that when we're finding an inverse, step number 1 is always going to be to switch the x and the y in my equation. That's equivalent to graphically reflecting the function over the line y equals x. So when I do this switch, I'm going to have x is equal to y over y minus 2. My second step is always going to be to then solve for y. But you'll notice that in this particular example, I ended up with 2 y's. So I'm going to start by cross multiplying. I'm going to call this an x over 1. When I cross multiply, I've got 1 times y equals y. Going the other direction, x times y minus 2. So let's distribute that and get xy minus 2x. Now since I want to solve for the y, I need to get the y terms both on the same side of the equation. So I'm going to subtract the xy so that it's now on the left side. And I've only got a negative 2x on the right side. That allows me to factor the y from the left side, so I'm going to say y is being multiplied by 1 minus x. And that's equal to negative 2x. To get the y by itself, all I need to do is divide both sides by 1 minus x. So I now have y is equal to negative 2x over 1 minus x. Now remember that if you graph both your original function on your graphing calculator and you also graph this inverse function that we have just found, what I should see on my calculator is that the original function and this inverse functions are reflections of each other over the line y equals x. Let's go ahead and try part B as well. So first step, switch the x and the y. X is equal to y plus 3 over 2y. Then solve for y, so I'm going to cross multiply and get 2xy equals y plus 3. There are 2 y's again, so I want to move the y terms both to the same side of the equation. Oops, that should be a minus y equals 3. Let's factor out the y, and that's what allows us to write this in inverse form. So I now only have 1 y, and I'm going to get that y by itself by dividing both sides of the equation by 2x minus 1. So my inverse equation should be y is equal to 3 divided by 2x minus 1. Sometimes we write the inverse in inverse notation. F to the minus 1 of x is equal to 3 over 2x minus 1. In example 5, we're given the function f of x is equal to x squared minus 8 over 4x. And we're going to go back to an idea that we learned in our transformation unit. We want to know, is this function even or odd? And then what does that tell us about what type of symmetry this function must have? You'll recall that when we were working with functions and trying to decide if they were even or odd, let's remember the definitions. For an even function, an opposite input would yield the same output. For an odd function, opposite inputs yield opposite outputs. So if we try 2 different numbers, we can try to solve this and explore it numerically. Say, well, let's substitute negative 1 in for x. When I substitute negative 1 in for x, I'm getting negative 7 over negative 4. So that's the answer, 7/4. Now, how about when I put a positive 1 in for x to see if it's the same or the opposite, or possibly neither? When I put a 1 in, I'm getting negative 7 over positive 4. So I should see that I'm getting an opposite answer when I had an opposite input. Let's just do one more. What if I try the number -2? -2 squared minus 8, that's giving me -4. -4 over -8 is positive 1/2. When I substitute a +2 in for x, I'm getting -4 over +8, or -1/2. So what this is telling me is that opposite inputs actually yield opposite outputs. So if that's the case, that tells me that this must be an odd function. Now lastly, let's recall that when I have an odd function, when I look at the graph, this should have symmetry with respect to the origin. So I would be able to take the graph and reflect it over the origin and get the rest of the graph. Thanks very much for working on rational functions tonight. We'll do some more work with these rational functions in class. If you have any questions, please be sure to come and see me during activity period so that we can get them cleared up right away at the beginning of this new unit. Have a great night. See you tomorrow.